I have a observation to make about your variational autoencoder lecture, which was fascinating, and I still have to wade through the math. I apologize. I have to make an intuitive a question about the intuition regarding variational autoencoders, and basically the main idea being that we go from a high dimensional space into latent space, and then we have to have a very particular type of latent space, and then we go from that to back into reconstruction and into high dimensional space. So the main intuition, at least how I perceive it, that of the motivation behind the variational autoencoders that I see is that in the classical autoencoders we have latent representations which are low dimensional, and in this case I drew a single dimension where we have a red data point, a green data point, and a blue data point in a latent space, single one-dimensional latent space. But when they're one-dimensional like this, there's basically no interaction between the representations of the latent space representations. There's no need for the similar representations to line up next to each other. Now, there may be a reason that this happens because the encoder might treat similar pictures in a similar way, let's say, and therefore it would put them close together. But there isn't any kind of incentive in terms of how we structure the latent space itself. Whereas with variational autoencoders, an interesting thing happens, and this is the intuition that I think is correct, but I'm not sure about it. So basically, variational autoencoders force a draw from a distribution and a definition of a latent variable as a distribution. So basically, when we have latent space variables represented as distributions as such, then neighbors can in fact influence each other in the sense that, in fact, if I have a dense enough data population of the space, and if the distributions have a wide enough standard deviations, then I will have situations such as this, whereby neighbors can in fact have overlapping distributions. And then it becomes important who the neighbor is. And because, and I'm not sure if this is what would happen, but if in fact variational encoders force this kind of overlapping distributions, then the neighbors, in some sense, would have similarity in whatever terms similarity is measured at the very end, I guess, L2 norm between reconstruction and original data input. So what we want is when we make a mistake, when we don't, when the decoder actually chooses to reconstruct a different picture, effectively, not the correct picture that was given, but neighboring picture, then it's important for that neighboring picture to be as similar as possible to the original input. And this may actually, if this is all true, this may give a further insight as to why blurriness is to be expected. Because if we in fact have a situation where we have an encoding that draws from a distribution, some picture gets encoded, then we draw from a distribution. That distribution to the decoder looks like a different one from a different neighbor, and we reconstruct that neighbor. It may actually be beneficial to blur that image, specifically for the cases where these distributions overlap, so that we again regain this, have a chance to gain back some of the points for, despite the fact that we have made a wrong choice. So that's just an intuition. I'm not sure if this any of this is really the case, but thank you very much. I think that's it.